The next topic is going to be everyone's favorite topic when they learn about routing. It is going to be routing protocol redistribution. And here we are going to talk about the concept of redistribution, what it is, how it works, what it does and what it doesn't do. We are going to take a quick look at redistributing connected and static routes, and even though it sounds like a simple process, there are little caveats there that you need to be on a lookout for. And then we are going to look at the redistribution between dynamic routing protocols. And finally, we are going to take a look at one of the most complex scenarios you can encounter in your networking, which is also fun, which is mutual multi-point redistribution. That is when we are going to be redistributing between different routing protocols at different locations, and we are going to end up having all sorts of loops in our network. Or we could end up having all sorts of loops, but we are going to try to avoid them. Simply speaking, route redistribution is the process of injecting the routes from one routing source into a dynamic routing protocol as external routes. Now, what is the routing source? The routing source can be any number of things that inject the routes in a routing table. It could be the connected routes, it could be static routes, or it could be another routing protocol. So when we have the process that routes are being installed in the routing table by one routing process, or routing source or routing process, by any of these sources, and then we configure another routing protocol, another routing source to actually take those routes and inject them as external routes in its own protocol database. This is the process that we call route redistribution. So if we take a look on the whiteboard and if we use an example of, for example, 3 routers, let's call them R1, R2, and R3 here, and let's say that R1 and R2 here are running, say, EIGRP, and let's say that R2 and R3 are running OSPF, and that means that R1 is injecting some routes in the EIGRP routing table. Let's say that there was a loop back here that was advertised to R2. If we configure the redistribution process on OSPF to redistribute EIGRP routes, what we are going to have here is the routes learned on R2 by EIGRP actually redistributed into OSPF. However, there is one however here, and that is that there is really no direct protocol-to-protocol route exchange. Now, if you take a look at here, I did mention that the routes are injected from the routing source into the destination routing protocol. In this example here, my EIGRP is the source and OSPF is the destination. And you would think that the routes were directly injected from the EIGRP topology table into the OSPF database as the external routes. That doesn't happen, however, and that's the reason why I put this tiny little asterisk here to explain it a little bit more here. The process that actually happens, with just 1 or 2 exceptions, is that the routes from the routing source need to go into the routing table, and then from the routing table they are redistributed, injected into the destination protocol. So this picture here is really incorrect a little bit. A more correct picture would be when we have routers R1, R2, and R3. So let's say that these are our R1, R2, and R3. And as I said before, let's say that R1 and R2 are running EIGRP, and that R2 and R3 are running OSPF. So here what we are going to have is the situation that R1 advertised some routes, like for example its loopback, to R2. R2 has these routes in EIGRP topology table, and as the result of that, it is actually going to calculate the routing table and it's going to install these routes in the routing table. But here we are going to have the information, we are going to have a trace information that these routes came from EIGRP. So if we go here on this OSPF process and we say, for example, router OSPF 1, and we say redistribute EIGRP, and let's say that there was an AS number 12 there, subnets, and I'll talk about this subnets keyword. What's going to happen here is the router R2 is going to take a look, it's going to ask the routing table, hey, give me all routes that are installed in the routing table by EIGRP 12. So here we are going to also have information that this came from EIGRP AS number 12. So routing table is going to then tell the OSPF process, there you go. These are the routes that I have that match the criteria. So these routes are now going to end up in OSPF database as the external routes, and as such will be advertised to R3 as type 5 or type 7 LSAs, depending on what kind of area type we had here. So it's important to understand that there was never direct route exchange between OSPF and EIGRP. This does not happen. The only exchange of routing was from the source, so this was still the source protocol that inserted the routes into the routing table, and from the routing table we had routes injected into the destination protocol database. Essentially what did happen here was that in the end we had the routes from some source protocol injected into some destination protocol. So you might be thinking to yourself, why do we have to bring this routing table into the mix? Isn't it easier to just think of redistribution in these terms here? Well, to a degree you would be right. Yes, it is easier to think of redistribution as the direct process where the routes are coming from the source and going into the destination, but you could be in a situation that you see in the protocol database of the source, you see certain prefixes, and when you do the redistribution, you would expect to see them in the destination protocol database, but they are simply not ending up there. And you might be scratching your head thinking, hey, hold on a second, there must be an iOS bug that I'm dealing with here, when there is no iOS bug. What you need to make sure is that these routes that you are looking at were actually installed in the routing table by this source protocol. If they were not installed by this source protocol, if they may have been installed by some other protocol, say that you wanted to redistribute from EIGRP into OSPF, but you had, say, RIP routes installed for whatever reason, not what you would want to have in your network anyways, but let's say that you did have RIP routes installed in the routing table, then your redistribution from EIGRP to OSPF, even though these routes exist in the EIGRP topology table, your redistribution won't do anything because the routes in the routing table were installed from another protocol. So this is really a fundamental thing in understanding how the route redistribution works. As I mentioned before, when we are configuring redistribution, what we are configuring is the destination routing protocol to import the routes from the routing source. So generically speaking, our configuration of the redistribution is going to be the router and then the destination process, so whatever it might be, say EIGRP or OSPF, and then we are going to configure the redistribution command. And this is the generic syntax of this command. So we are going to say redistribute routes from the source. We are going to have some destination options in the case of some protocols that have specific options. Like for example with OSPF, we can specify whether we want to redistribute the subnets of the classful networks, which is something that I highly recommend you get in habit of doing. And then we can specify the metric, and if we want to selectively redistribute the routes, we would use the route map. So let's take a look at, for example, EIGRP. For EIGRP, the thing to keep in mind when configuring redistribution is that there is no default seed metric. Now, what is seed metric? It's this part here. When we inject the routes into the routing protocol, when we configure the redistribution, what we are doing is we are taking the routes from another routing source that have some sort of metric from that other routing source, for example, OSPF cost or calculated BGP attributes, or whatever that metric might be. But when we are injecting these routes as external routes into another process, those metrics are not compatible. So we have to tell the target process, our destination process, we have to tell it which metrics to use, what is going to be the starting point for these routes. And this is going to be this metric that we are specifying here. And for some routing protocols, there are defaults. For EIGRP, there is no default value here. And by the way, the name of this metric is sometimes called, this metric is sometimes called the seed metric, because this is how we are injecting the routes in there. Now, why is it significant that for EIGRP there is no seed metric? It's significant that is because if we simply did redistribute source without specifying the metric on the command line, the redistribution line will be there in the running configuration. But since there are no metrics associated with those routes that are being redistributed, EIGRP doesn't know how to insert them into the EIGRP topology table. So you are going to have the situation that you do see the redistribution configured in your running configuration, but no routes are actually being injected into EIGRP. To avoid that, it's a good thing to keep in mind, or always remind yourself that when you are redistributing into EIGRP, always specify the metric. And the metric in EIGRP is specified using the metric component. So we have to specify the bandwidth, delay, reliability, load, and the MTU. As you might remember, there is one more hop count, but the hop count for these routes will be 1 at this stage, because you cannot directly influence the hop count. So this is one way you can inject the routes into EIGRP. Another way is to use a default metric command. Default metric is the command in which you can specify the default values, and here I prefix them with the lowercase d, so that we can say whenever we redistribute routes into EIGRP, use these metrics for the seed metric. In that case, just doing redistribute from a particular source will be effective, because these values here will then be used for the metric. Now, these can coexist just like I did here. So here we can see that we have redistribution configured from two sources. For these routes here, for this redistribution from source 1, these metrics will be used because they override whatever is set for as default. For these routes from the source 2, of course, the seed metric specified in the default metric command line will be used for redistribution. OSPF in this sense is much simpler protocol to work with. There is default metric, and it will be 20 for all the redistributed routes except for BGP. The BGP redistributed routes will have the default metric of 1. The metric type, and you might remember that there is type 1 and type 2 in OSPF. The default metric type will be 2, but you can specify and change this. So this is the generic syntax for OSPF. Redistribute from a particular source. I highly recommend that you always get in habit of using the subnets keyword, and then you can optionally specify the metric, you can specify the cost, and you can optionally specify the metric type. Now, for OSPF, if you don't specify the metric or the metric type, because it does have built-in defaults, your redistribution will be successful even if you just did redistribute source subnets. Let's now take a look at some of the considerations that you need to take into account when redistributing connected routes. Connected routes, just like any other routing sources, can be redistributed into any routing protocol using explicit act of redistribution. Now, what I mean by explicit act of redistribution is going into the router, which is going to be our destination process or router destination, whatever process that might be, and we simply say redistribute connected followed by protocol specific parameters. And protocol specific parameters are the things that we just discussed earlier. Now, this is when we want to redistribute connected routes. Obviously, I'm not talking about using the network statement, which in a sense is also going to inject the connected routes into the routing protocol, but network statements are going to inject the routes as protocol internal routes. When we talk about the redistribution, we are talking about injecting those prefixes that are associated with local interfaces on the router as external routes to the protocol. Now, there are some protocols like, for example, RIP. Well, actually, come to think of it, it's the only protocol that do not have or do not understand the concept of external routes. In that case, using the network statement or redistribution of the connected routes is the same. But there is another way of redistributing connected routes, and that other solution is something that I like to call the implicit redistribution. This is very involved, and this is not very involved, but it's very, very important concept to understand. What this is when we are redistributing from one dynamic routing protocol into another dynamic protocol, by default, what's going to happen, all those networks associated with the interfaces enabled for the source dynamic protocol will also be redistributed. So what I mean by that is when we say router destination redistribute source, what's going to happen here is not only the source learned routes are going to be redistributed, but also all interfaces enabled for the source. Let me explain this in a little bit more graphic way. Let's say that we had three routers, R1, R2, and R3. And let's say that between R1 and R2, we were running EIGRP, and let's say that this is going to be AS number 12, and let's say that here we were running OSPF in area 0. And let's also assume that on R1 we have some loopback interface with the IP address 10.0.0.1/32, and let's say that this here is 192.168.12.0/24, and that this here is 192.168.23.0/24, and this here is going to be gigabit interface 1, gigabit 1, gigabit 2, and gigabit 2. Obviously, the IP addresses here are .1, .2, .2, and .3. So let's say that our EIGRP and OSPF are configured, but there is no redistribution involved. Also, this interface here, 10.0.0.1/32, is being injected into EIGRP as an EIGRP internal route, which means that on R1 we have the network statement. Let's now go ahead on R2 and configure the redistribution from EIGRP into OSPF. So very, very straightforward configuration, nothing special there. So the configuration here would be router OSPF 1, and let's say redistribute EIGRP 12 subnets. So this is the basic redistribution configuration on OSPF. So now what's going to happen is from the routing table on R2, the routes that were injected by EIGRP are going to be inserted into the OSPF database on R2 and then advertised as external LSAs to R3. So what are those routes going to be? Let's take a look at this. I actually have this example configured, everything except the redistribution part. So if I go to my terminal here on R2, if I do show IP route connected, I'm going to see that I have my 12 network and 23 network there. If I do show IP EIGRP neighbors, I see that I have one EIGRP neighbor, and if I do show IP OSPF neighbors, I see that I have one OSPF neighbor here. So on R2, if I do show IP route EIGRP, what I'm expecting to see here is really just one route. What I'm expecting to see is the loopback of R1, because this is the only route that was actually advertised by EIGRP. This route here, 192.168.12.0, is a connected route on R2. Let's now go ahead on R2 and let's just briefly take a look at the process. Here it is. Let's just configure basic redistribution. So I'm just going to say redistribute EIGRP 12 subnets. So now if I go to R3, if I do show IP route OSPF, what I'm expecting to see here is really the loopback address of R1. if I go on R3, I am going to see it, here it is, but I'm getting something else. I am getting this 192.168.12.0/24. So this network here, associated with this interface was also redistributed. Now, this is what I meant when I said that implicit redistribution of connected routes will include networks associated with interfaces enabled for the source dynamic protocol. What we had here was that this gigabit interface 1 was enabled for EIGRP, and when we said redistribute from EIGRP into OSPF, not only the learned routes in that process were redistributed, but also the connected routes associated with these interfaces. It is also very, very important to understand that this is going to be overridden by the explicit redistribution command. Now, what does that mean? Well, to take a look at that, let's expand our example here a little bit. And I have to clean it up. I'm running out of places to draw here. So let me just redraw that. So I have R1, R2, and R3. So we know that here we have EIGRP 12 and that here we have OSPF area 0 running, and we know that we have this loopback interface here. So let's now go on R2 and let's create two loopback interfaces. So these two loopback interfaces, I'm not going to associate them with any routing protocol. So let's create, for example, 10.0.0.2/32, and let's configure 10.2.2.2/32. So this here is going to be, let's say, loopback 0, and let's say that this one here is going to be loopback 2. So what I want to do now is I want to configure my R2 to redistribute only this loopback into OSPF. Mind you, when I say redistribute, I mean redistribute. I'm not going to be using the network statement. But what I want to not redistribute is this loopback here. So let's see what needs to be done here. Well, what I need to do here is I need to create some sort of a redistribution filter, and we know that we can apply a route map at the redistribution point, which is perfect. So I'm going to create, for example, route map, and let's call it connected or just con, and I'm going to say match interface loopback 0. And then I'm going to go to router OSPF 1, and I'm going to say redistribute connected subnets and route map connected or con. So this is the configuration that I'm going to do. So as you can see, very, very straightforward, very, very simple configuration. I'm not going to change anything else. So let's head to our R2 now. And I'm going to start by creating my interfaces. So interface loopback 0 IP address 10.0.0.2. And interface loopback 2 with the address which is remarkably similar to this one. So if I do show IP route connected, this is what I should be seeing. Now on R3, if I take a look at show IP route OSPF, I'm seeing no changes, which means that this is the situation as we have it right now. So then I'm going to create my route map. So let's create route map connected, and I'm going to say match interface loopback 0. Then I'm going to say router OSPF 1, and I'm going to say redistribute connected subnets route map connected. Now if I go to R3, and I have to wait about 5 or 6 seconds before I take a look at this, so about now, this is what I have in my routing table at the moment. What I do have is the loopback of R1, which I had before, and I expect to see it because this was originally EIGRP route. Now I'm getting the loopback 0 of R2, which was the connected route on R2, but what I'm not getting anymore is this route here. This route is now gone. Why is this route gone? Well, if I take a look on R2, that is a connected route on gigabit interface 1. Now, when I configured the redistribution from EIGRP into OSPF, this interface here was redistributed implicitly as the connected route because it was enabled for this particular source protocol. However, the moment I have issued redistribute connected command for the OSPF process, this interface here is no longer considered as an EIGRP route for the purposes of redistribution and is now considered to be the redistribute connected. It is now considered for the redistribution into this OSPF process as a connected route, which means it is going to be a subject to the filtering specification. And in our filtering specification here, what we have said is allow interface loopback 0 to be redistributed. At the end of this, there is an implicit deny everything else statement in the route map, which means that this interface here, loopback 2, will not be redistributed, but neither would gigabit 1 because we have not allowed it to be redistributed. So when we are configuring our redistribution of connected routes with this explicit redistribution of connected routes with this part here, this configuration will override the implicit behavior here. Another thing that I would like to point out here, and it here says this on the slide, so this is something that you should remember, you should keep in mind. First of all, this behavior affects all protocols that are enabled on particular interfaces on per interface basis, which means that this affects all IGPs. The only exception to this particular behavior is the BGP, which is not enabled on per interface basis but on per neighbor basis. And this is the behavior that is perceived, that is the same across all iOS versions. Well, all starting 11 something up until 15.4.1, which is the latest one that I have tried this in. This is experienced by all the protocols in all versions of iOS, so no exceptions. And this is the behavior that can cost you some headache, because if you were working in a network that required full reachability between your domains, everything else, by configuring this filtering, this sort of redistribution here, you might get rid of this route. So it's very, very important to know that when you're configuring the redistribution of connected routes and when you are associating any sort of filters there, make sure that those interfaces that you actually do want to redistribute, that you include them in the filtering. Another thing that I would like to point out, that this is not only the same behavior for all the protocols and in all iOS versions, but it doesn't matter how you actually implement filtering in the route map. This is always going to be the same thing. Are you implementing the filtering using match interface? Are you using access lists or prefix lists? It doesn't matter. The behavior will always be the same. So let's correct this. I'm going to now go into my route map connected, and I'm just going to add match interface gigabit 1. So I'm going to include one more interface. And if I do here, if I take a look at the configuration of the route map now I see that I'm actually including two interfaces, loopback and gigabit 1, which means when I go to R3, if I do show IP route OSPF, now I'm going to see two of my connected routes, two of my loopback interfaces, and also the connected route between R1 and R2. When it comes to the redistribution, static and dynamic routes in iOS are treated remarkably similar, or I should say identical. There is really no difference in how the process works, redistributing static or dynamic routes. You just have to remember one thing: no matter what kind of route you are redistributing, is it a static route or is it a dynamic route, it is always redistributed from the routing table and then into some dynamic protocol, which would be our destination routing protocol here. Now, I'm singling out static and dynamic routes. What about connected routes? How are they redistributed? Well, think about it. Can we have a connected route that is not in the routing table? Well, the only way we can have it is if this interface is shut down. In that case, the route disappears from the routing table. And even the connected routes are treated the same way. If the route is not in the routing table, and in a case of connected routes, that means if the interface is shut down, this route will not be redistributed. Same thing goes for static and dynamic routes. But static routes, due to their, well, static nature, they may require a little bit more look into the dangers of thinking that you are redistributing static routes when you are in fact not doing that. To take a look at that, I'm going to expand the example that we have been using so far. So I'm going to be using my three routers, R1, R2, and R3. What I'm going to add now on R3 is going to be interface gigabit 3. Now, this interface is going to be connected to something, some layer 2 device. So there is really nothing on this side here, just something that is going to cause the interface to come up. And I will configure on this interface the IP address 10303/24, and I'm going to pretend that there is some device with a 254 IP address here on the other side here. Let me go away for a second there. So this is what I'm going to be doing now. What I'm going to be doing next is I'm going to add a static route on my R3 pointing to this interface, to this IP address as the next hop for example, 172.16.00/12 network. So I want to add this static route here, and then I want to redistribute this static route into my OSPF that is already running and is configured here. So let's take a look at that. Here on R3 now, I'm just going to say show IP route connected. I want to make sure that my gigabit interface 3 is up and running, and I can see it here. It is up and running, and it does indeed have an IP address that I wanted to have. So what I'm going to do now is I'm going to add my 172.16.00/12 route, and I'm going to point into the next hop of 10.3.0.254. As I said, this host doesn't really exist, but the only thing that I need here is a valid next hop. What is a valid next hop from the perspective of static routes? It's the next hop for which we do have a route, and in this case we do actually have the route here. So if I do show IP route static, I'm going to see that this route is now inserted into my routing table. So let's go to OSPF now, and I'm just going to say redistribute static subnets. Now keep in mind that the default in OSPF is to give me the metric for this. So let's confirm that. So if I do show IP OSPF database external self-generated, what I'm going to be seeing here is that I have the metric 20 and it is type 2 metric, so I can see that this prefix was actually installed in OSPF. And here on R2, I can see that I actually am receiving this external route. Now, let me add another static route. So I'm going to say IP route 172.16, let's say 00/24. And this one, I want to point to the next hop of 10.4.0.254. So if I do show IP route static, this route is not going to be in the routing table. Why is this route not going to be in the routing? Actually, you know what? I made a mistake here. I just realized I actually used the wrong mask here. I wanted this to be inserted as /12, and I actually inserted it as /20. Let's fix that. Oh, I don't want to leave this incorrect like so. So let's fix this one here, and let's remove the wrong one. So what I want to do here now, oh, apologies for this, but you know, we all make mistakes. So if I do show IP route static, now I see 172.16.00/12. That's correct. But let's go back to the example that I was just showing you. So here is a new static route that I added. So I added this one here, /24, which is more specific, and we should be seeing it in a routing table. But we are not seeing it in a routing table because this next hop here is not valid. So this route will not be inserted into the routing table. if it's not in the routing table, the fact that we have it in the static routing database, which for static routes is the running configuration, doesn't mean anything. This route will not be redistributed. And if I do show IP OSPF database, here in the type 5 external routes, I can see only 172.16. We can see only one type 5 LSA for this route. And this is what I wanted to show you for static routes. The fact that we have it configured doesn't mean anything. Just like any other routes, it needs to be in the routing table. So let's say that we did indeed make a mistake, that we wanted this route to go into the routing table. So let's fix it. So what I'm going to do now is I'm going to remove the incorrect route and let me add the correct route. So now if I do show IP route static, I'm going to see that I do have two routes. One is /12 and the other one is /24. If I go to R2, I'm going to see in the routing table, in the OSPF table, on R2, two static routes, because now on R3 I do have two static routes in a routing table, and they are both being redistributed. So what if I actually didn't want both of them to be redistributed? What if I wanted to implement some sort of a filtering there in place? Is there something that I can do about it? Well, of course there is. What we can do is we can filter the routes. So we already know one method for filtering the routes, and that is at the redistribution point, specify the route map, and in a route map use whatever match statements. But now I'm going to show you something else. Imagine that our R3 here was a redistribution point for many different static routes. So we had many different static routes configured. So these are all static routes. Now, what I want to do here, instead of using the route map, I want to configure this in such a way that whenever I'm redistributing static routes into OSPF here, I redistribute those static routes that match a particular access list, let's say access list 10, but I don't want to use the route map for this purpose. Now, that means that if I do redistribute static, here, if I use the route map, I would break my own rules here. So I don't want to use the route map. So if I cannot filter here at the redistribution point, is there something else that I can do? Well, you remember how we filtered the routes in dynamic routing protocols. We use distribute lists. Now, the distribute lists can actually be used for the purposes of redistribution. And the reason why I'm singling them out here is because they are used in slightly unusual way. So what we need to do here is we need to put ourselves, when we want to use distribute lists for the redistribution filtering, we need to put ourselves in the position of the routing table, because this is where the filtering will happen. From the routing table out into the particular protocol. So what we need here is a distribute list applied in the outbound direction from the routing table. But how do we actually configure distribute list in the routing table, generally speaking? Well, that's the problem. We cannot. But what we can do is we can configure something that is actually going to do this in the router process that is actually the destination for our redistributed routes. Let me show you that. So going here on R3, let's first create an access list. So I'm going to say access list 10, and let's say permit 172.16. And just because with the access lists I cannot match the prefix length, let's do another route here. So I will add this static route here, and let's add it. So IP route 172.16.100.255.255.255.0 and 10.3.0.254. So if I do show IP route static, I can see that this route is here. So if I go to router OSPF1, I can do distribute list 10 out. And here, if I take a look at the question mark and the possible options, I'm going to have this list of protocols, for example, OSPF, RIP, static, and so on. I even have EIGRP and BGP and ISIS here. So this is where I can say static. So now what I'm telling my router is take those routes that match access list 10 and advertise only those, redistribute only those from the static source. That means in the routing table, match the routes that match the access list 10 and only redistribute those into OSPF. So if I do show IP OSPF database external self-generated, now I will see that there was only one route here that was allowed, and that was our 172.16.100. Now, you know that with access lists, we cannot match the actual net mask. And I talked about this when I talked about different filtering in EIGRP and OSPF, so I'm not going to repeat myself here. But if I wanted to match a particular prefix, here with this distribute list, so let me remove it, I could have used the prefix list. So let's say IP prefix list, let's call it prefix list 1. I can say permit 172.16.00/24. So I can do this, router OSPF1, distribute list prefix PL1 out from the static source. So now if I do show IP OSPF database external, self-generated routes, oh, okay. Let's see, this is actually, I need to wait a little bit for the older routes to disappear, and there it is. Now it did clean itself out. So now here I can see that this did get redistributed. Now it says here that 172.16.0255 is the external network number. This is a little bit wrong because this is incorrect. I have no idea why that happens, but here in my routing table here on R2, I see the correct route in place. This is really interesting. Why would it show it like this? I guess that I may have found an interesting bug in OSPF here, but I'm not going to stress about it. The important thing is that the route did get advertised, and quite frankly, what it says here in the last octet is really relevant because the correct network and the mask will be calculated based on the prefix length. But what we can see here is that my distribute list applied in the process here did work. But there is another interesting way to filter the routes when redistributing them, and that is to use the concept of route tags. Route tags are pieces of information, just identifiers, additional numbers that are carried on the routes that may be used for filtering purposes. So let's say that we had some routes here. So let's say our static routes here. Let's say that one of them had a particular tag. So let's add the tag on this one. Let's say tag 55. So tag is just a number. So if I do show run include IP route, here I can see that this route now carries the tag of 55. Now, with route tags, what I can do, let's say that I wanted to redistribute only some of those static routes that are tagged, but I don't know what are they going to be. So they can be any route, so I don't want to maintain my access lists or prefix lists. I'm just saying I will be redistributing only those static routes that have this particular tag. So how would I do that? With that, unfortunately or fortunately, you need to configure the route map. So what I'm going to do here is I'm going to configure route map, let's call it from static, and I'm going to say match tag 55. As simple as that. And then I'm going to go to router OSPF1, and let me take a look at what is my configuration now. And I'm going to remove this distribute list, and then I'm going to say redistribute static subnet route map from static. So now if I go to R2, if I do show IP route OSPF, I can see here that I have 172.16.100 network. But if I wanted to, for example, advertise one more of these, all I have to do really is just add tag 55. And now if I do show IP route, I can see that this route now made it through. It made it through because this route did carry the tag. Now, when we take a look at the routing table, we cannot easily see the tags. If you wanted to see the tags, we would actually have to look into the route itself. We would actually need to look for a specific route, and here we have the information about tag. These route tags that can be used for static routes, for example, can also be used for dynamic routes. And they offer an extremely flexible way for filtering the routes at redistribution points because you don't have to keep track of particular routes that you want to redistribute. All you have to say is just make sure that you are redistributing only the routes that carry this tag that we are interested in. And the tag can be any number you desire. Let's now take a look at some of the more advanced redistribution concepts. Now, these are not going to be too advanced, but they are important to understand. The first thing that I want to talk about is something that I like to call a routing domain. Now, when it comes to redistribution, all routes that are being redistributed are coming from a particular source. Now, what is this source going to be? It can be anything, but when we are talking about routing domain in terms of redistribution, we are usually talking about the protocol. So let's say that we had some routes and they were all belonging to EIGRP. We can say that at this location here on our R1, we are going to be redistributing our EIGRP routes to, say, OSPF. So here we might define all EIGRP routes, regardless of which router they are actually coming from, as belonging to a single routing domain. Similarly to this redistribution router R1 that is obviously running both EIGRP and OSPF in redistribution terms is a little bit special. This is something that we can call a redistribution point. A redistribution point is simply a router that runs both source and destination protocol and that is performing a redistribution of routes between them. But how can this redistribution of routes be done? Well, there is something that we call unidirectional redistribution, which is when we take the routes from one protocol and we redistribute them into protocol 2. In other words, we are simply going to redistribute in one way. Examples that we have done so far have all been examples of unidirectional redistribution. Another, a little more advanced concept is mutual redistribution. This is when we have this device, let's say our R1 here, that is connected to both EIGRP and OSPF, and is not only redistributing from EIGRP to OSPF, but is also redistributing from OSPF back into EIGRP. So if we have this situation that we have two routing domains that are mutually redistributed, this is something that we call mutual redistribution. And this mutual redistribution can be single point or multi-point redistribution. What do I mean by that? Well, let's say that we had two routing domains. Let's say that we had EIGRP and OSPF. If we had a single device, a single router sitting on the boundary between these domains and was redistributing like so, we can say that we have a single point mutual redistribution. When we have a single point mutual redistribution, really there is nothing important that we have to worry about other than configuring the redistribution properly. However, if we had a situation that we had two routing domains with multiple redistribution points between them, so let's say that we had routers that were redistributing like this, this is something that we call a multi-point mutual redistribution. This is something that whenever you encounter in either your network studies or in production environments, or if you are preparing for your CCI lab exam in particular, for example, this is something that you need to be on a very, very, very high lookout for. This is danger, because what is happening here there is a distinct possibility that we are going to have a route that starts its life here in this routing domain here, that it goes out to this router, is going to get redistributed here, and then travel back to this router here, and at this redistribution point here, be injected back in. Now, when we have that situation, what we are doing is we are really creating a routing loop here. Now, keep in mind that most of the routing protocols you are ever going to deal with, like for example EIGRP or OSPF, or for that matter ISIS, they all make a distinction between internal protocol routes and external protocol routes. However, there is one protocol that doesn't make that distinction, which is RIP, and also to some extent BGP. It only makes a distinction between internally learned or externally learned routes, but BGP is a special case. Whenever we are talking about the redistribution, we are never really concerned about BGP. We are only concerned about the internal gateway protocols, about our IGPs. So if the routers are making the distinction between internal and external routes, when we have that situation that we have mutual redistribution at two locations between two protocols, we really have no danger in creating a loop. Why is that? Well, if we have an internal route in this protocol here, whatever this protocol might be, when it goes this way and this route arrives here, this route here will now be injected as an external route in this protocol here. So regardless of which protocol we used, whether this was OSPF or EIGRP or ISIS for that matter, but again, let's not concern ourselves with ISIS at this moment, we are not going to create the loop. Well, unless this route here, to begin with, was an external route. Let me give you a scenario for that. Let's say that we had a router here that is connected to, let's say, some internal network somewhere, and that these two routers here are our redistribution points. And let's say that here between these routers, let's say that here we were running EIGRP. Let's say that here we were running OSPF. Actually, you know what? Let's say that we are here running OSPF. And let's say that here we are running another EIGRP process. And let's say that this router here was injecting some routes. So we have EIGRP process running on this router here and on this router here. Let's give them some names. So this is R1, let's say R2, R3, R4, R5, R6, R7, R8, and let's say R9. So here we have some route that is, let's say, an internal EIGRP route. It's an internal EIGRP route on R2. And then this route is going to be injected into the OSPF domain with some seed metric. Now, this seed metric is going to be preserved as this route arrives to R5 and as this route arrives to R6. Now, R5 and R6 are going to inject this route into EIGRP domain. Let's say it was R5 that was doing this. So it's going to inject this into our EIGRP domain as some sort of an external route. So this route is now going to travel back to R6, where R6 may learn it as an EIGRP route. Now, if router R6 learns this as an external EIGRP route, and let's say that for whatever reason on R6, we lowered the admin distance of external EIGRP routes to be below 110, or R6 wasn't receiving these routes here. Let's say that R6 here was in NSSA area. Perfectly legitimate situation to have. So R6 here was in NSSA area. So it wasn't actually receiving this external route to begin with here. So this external route never actually arrived to R6. Now R6 may be configured to inject this route back in, but let's say that this seed metric here is considerably lower than this seed metric here. What that means is that this route is now going to travel through OSPF domain, and it's suddenly going to appear as much better route, say on R3. Now, what's going to happen with the traffic, or on R4 for that matter? Let's say that this route now arrives to R4, and R4 now needs to send the traffic following this route. So it's going to send it to R3, R3 is going to send it to R6, it's going to go all the way back to R5, who is going to send it to R4, and then this way, and this way, and this way, and this way. Now, keep in mind that this scenario that I just described, you've seen how many things here, how many little pieces here needed to assemble for the trouble to begin with. So here we first needed to have the external routes. We needed to have some sort of a relatively low seed metric. Then we needed to have a special sort of configuration here, or the admin distance changes, and this, and this, and this, and this, and this. So many little things need to assemble for the loop to be created. So this is not given that you are going to have the loop. But whenever you have a situation that you have a multi-point redistribution, multi-point mutual redistribution, be on a lookout that loop is possible. And if the loop is possible, how do we prevent these loops from happening? Well, what we need to do here is relatively simple thing. So let me just again redraw our examples here. I'm just going to make a very simple example here. When we have this mutual redistribution at multiple redistribution points, what we need to make sure is when we have these two protocols involved, so let's say that this is protocol 1 and that this one here is protocol number 2, what we need to make sure is that the routes from protocol 1, when we are redistributing these routes back into protocol 1 from protocol 2, that these routes don't make it back. And the same thing here for the routes from protocol 1, as we are redistributing them back into protocol 2 from protocol 1, we need to find some way to actually prevent this from happening. Now, there are multiple ways we can do that. We can use access lists, we can use prefix lists, and we can use both these with either distribute lists or route maps. But usually the most scalable solution is to use route tags. So I already talked a little bit about route tags, but this is where route tags actually excel. This is where route tags actually have the biggest strength. So let me show you that example. Let's say that we had these two routing domains with two routers that were redistributing mutually between these two routing domains. So we have this redistribution direction and we have this redistribution direction here. Now, at this location here and this location here, we need to implement filtering. So let's say that this one here was OSPF and let's say that this here was EIGRP. What we need to do here is we need to create some sort of a filtering policy that is going to deny original EIGRP routes. That means that routes that may have been EIGRP that have gone out to OSPF and are now trying to come back in either this direction or this direction here, we need to make sure to deny these routes, and we basically need to permit everything else. And everything else are going to be OSPF routes. Now, the filtering policy that we need to implement on these two locations is the exact opposite. We need to deny the original OSPF routes, and we need to permit everything else, which would be, in this case, the original EIGRP routes. That means the routes that originated in the EIGRP domain, not the ones that were maybe learned from OSPF and then advertised back in. Now, keep in mind here that I don't care if these routes in OSPF are internal or external, and the same thing in EIGRP, as long as we are not talking about these routes at this point. If this is the case, then we need to add a third router here, because that would be a third redistribution point. So whenever you are analyzing the redistribution scenarios, you have to keep in mind all the redistribution points. So how do we solve this using route tags? Well, what we can do here is we can decide that when we redistribute these routes, instead of simply permitting OSPF routes, let's tag these routes as OSPF routes. And on this side here, let's tag them as EIGRP routes. So which tag values can you use? Well, you can use 1 and 2 here, or you can be a little bit more pragmatic and use, for example, route tag 110 here and route tag 90 here. With route tag 110 and 90, when you are using the same values as you have for admin distance by default, what you are telling yourself is immediately when you look in the routing table and when you see external routes, if they carry tag 110, you know those were original OSPF routes, or if you see route tag 90, you know that these were original EIGRP routes. So let's write down the policies here on R1 and R2. So this is going to be our OSPF to EIGRP policy. So what is this policy going to look like? Well, let's take a look. So let's write it down here. I'm going to type because it's much easier to type than to actually decipher my handwriting. So I'm just going to move this somewhere where you can actually see me typing. Actually, I'm going to disappear now. So here what we are going to have is route map OSPF to EIGRP. And the first statement is going to be deny 10. And what I'm denying here is the tag, the original EIGRP tag, and my EIGRP tag is 90. So what I want to do is I want to deny the routes that are EIGRP routes, and I want to make sure that everything else is first of all permitted, and then that it actually gets tagged as the OSPF route. So this is my policy for, this is my route map that I can apply on this filtering direction and in this filtering direction here. So on this side, let me try to find a place where I can put it. So on this side, I'm going to have similar but slightly different policies. So here, I'm going to have EIGRP to OSPF deny 10, and this changes to 110, and this is also EIGRP to OSPF permit. Actually, slight mistake, this needs to be 20, and this here needs to be 20. So now that I have these two, so let me actually copy this, and what I'm going to do now, just going to cheat a little bit. And now that I have this policy here, so these are both of my route maps now in a single place. So what I want to do next is, let me show you, let's say on R1, how the configuration for the routing protocol would look like. So here I'm going to say router OSPF1, I would say redistribute. Redistribute EIGRP, and let's say that we have EIGRP 100 metrics, or actually subnets, route map EIGRP to OSPF, and then on EIGRP process, so router EIGRP 100, I would say redistribute OSPF1 route map OSPF to EIGRP. Now keep in mind that for EIGRP we need to set some metrics, so we might as well use the default metric command. So default metric delay 100 is fine, 2551, and then 1500 for the MTU. So this is, for example, a good way of configuring this redistribution between these two routing domains to avoid the route loop from being created.